Okay, so today we'll continue our discussion from the example from Tuesday. Yeah. So let me also write down the problem that we covered. So the topic is still on the maximum likelihood estimation. And the problem that we work on Tuesday is the following. So let x1 and xn be IID random sample from a normal distribution with mean, mu, and the sigma square. And then the question is asking you to find the MLE, the maximum likelihood estimator of mu and sigma square. So I think last time we derived the mu hat and the sigma square hat. And we also checked that for the MLE of mu, which is unbiased and efficient and consistent. So that we already covered. So now the problem or the remaining component is referring we should work on the sigma square. And then for the sigma square, we also have a estimator. Let's denote MLE in the subscript, which has the formulation for summation from 1 to n xi minus x bar. So at the beginning, you will have xi minus mu, but this mu is an unknown quantity, so we have to plug in our MLE estimator. And maybe let me write it here. So we have to plug in our estimator for the mu to get the estimator for the sigma square. And then our mu hat is equal to x bar, so that's why we have the formulation of 1 to n xi minus x bar after you plug in your estimator for the mu hat. So this will be the expression that we are working with. Yeah. And just to reiterate a little bit from the end of the last lecture, we show that the expected value of this maximum likelihood estimator for sigma square is not equal to the true value. So this is not an unbiased estimator. That is what we discovered last time. So what it turned out is that the expected value for this maximum likelihood estimator is equal to n minus 1 sigma square. So it's not equal to the sigma square, so it's not an unbiased estimator. And we also mentioned that there's one way that we can correct this to make it an unbiased estimator, which is what we define as S squared in the following way. So sum of xi minus x bar over n minus 1. So our maximum likelihood estimator has a denominator equal to n. And then our new defined estimator has a denominator of n minus 1. So in this way, when you take the expected value for S squared, you will have 1 over n minus 1 and then the n minus 1 sigma square. And this is equal to the sigma square. So by constructing your estimator in this way, you obtain a unbiased estimator. So we can say that S squared is an unbiased estimator of the true value sigma square. So the conclusion here is that the maximum likelihood estimator is not an unbiased estimator for sigma square, but the S square that we define in this way is an unbiased estimator of the sigma square. Okay, so that is what we have from last time. So we have checked that this is unbiased. So now we want to check whether the S square is efficient or if it is a consistent estimator. Just like what we did for the mu hat. For mu hat, we already showed that it's unbiased, it's also an efficient estimator, it's also a consistent estimator. So for S squared, we need to do the same, and then we show that it's unbiased after we make the correction. And now we want to check whether it's efficient or whether it's consistent estimator. Okay, so before we do that, one thing that we want to, or I want to talk about, is that I want to provide you the distribution of S squared. And the reason for that is that you might need to use the distribution of S squared in the midterm or in the homework. Yeah. So so that will be our topic for now. So from previous lecture, we know that the n-1 multiplied by S squared divided by sigma squared. So this thing, we prove that it follows a chi-square distribution with degree of freedom n-1. Okay, so that is a proof from previous lecture. And now our interest is this particular component on the numerator, which is S squared. So what we want is the distribution for S squared only. Okay. And then we can show the distribution of S squared through the moment-generating function. So for chi-square, which is also a special case of a gamma distribution, so that we know that the moment-generating function, or so if x following, or maybe I can directly write it here. So that the moment-generating function of n-1 multiplied by S squared over sigma squared, which is a function of t, is equal to the following. So 1 minus 2t raised to the power of negative n-1 over 2. So chi-square is essentially a special case of a gamma distribution with the alpha equal to n-1 over 2, and the beta is equal to 2, because the moment-generating function for the gamma distribution is 1 minus beta t raised to the power of negative alpha. So here, the alpha on the exponent is the n-1 over 2, and the beta is the 2 in the parenthesis, so that this is the distribution for chi-square with degree of freedom n-1. Okay. So that means we also know that the moment-generating function for this particular quantity is equal to 1 minus 2t raised to the power of negative n-1 over 2. And now what we want is the moment-generating function for S squared. So what we can do is to write the moment-generating function as the following, as a coefficient, like a constant, multiply by n-1 S squared sigma squared. So you can think of this as like a constant multiplied by x, by a random variable. And then here we can use the property for the moment-generating function, which is the moment-generating function for ax is equal to the momentary function of the random variable x, but we multiply the a to the variable of t. So this is the property of the momentary function, and that is what we are going to use to find the momentary function for s squared. So essentially, you can think of this as the constant a, and then this as your random variable x, and then this is a function of t. And then this is equal to the moment-generated function of n minus 1 s squared over sigma squared. But the t has to be multiplied by the constant that we introduce. And now we can use the moment-generated function for this one that we know of to find the moment-generated function of s squared. So by simplifying the left-hand side, this should give you the moment-generated function for s squared of t. And now we plug in the new t. So you can call this the t star. And then you can bring in the t star into this momentary function, which is 1 minus 2t star. And then this t star is the sigma square over n minus 1 multiplied by the original t. And then with the same exponent, n minus 1 over 2. And then from here, we have this momentary function becomes 1 minus 2 sigma square over n minus 1 multiplied by t, and then negative n minus 1 over 2. So this is the new momentary function for the variable s squared. As we stated here, the right-hand side is equal to the momentary function of s squared. And now we can use this formulation to recognize the distribution for s squared. So here will be our new beta star, and then here will be our new alpha star. So then we can conclude that the s squared also following a gamma distribution with the new alpha equal to n minus 1 over 2. And then the beta is equal to 2 times the sigma square over n minus 1. Okay, so this is the distribution for s squared. So just to reiterate, what we are doing here is that we know that this one that we proved from before is that it's following chi-square distribution, degree of freedom n minus 1, and then which is a special case of a gamma distribution. And now we are interested in the distribution for s squared. So we can use the moment-generated function for a known quantity, and then after some manipulation to obtain the moment-generated function for s squared. And then that is the distribution for s squared. Although it's just also a gamma distribution, but with new alpha and beta. Is there any question regarding this part? So the reason why we want to derive the distribution for s squared is that when we want to check whether this is an efficient estimator, we want to find, or we need to evaluate the variance of s squared. So if we do not know the distribution for s squared, then we may not be able to find the variance of s squared. So that's why we want to talk about the distribution for s squared first, in order to ease our computation on the variance of s squared. And then the variance of s squared, if it achieved the Cramer-Rao lower bound, then we can comment on that S squared is an efficient estimator. So that will be our strategy for checking the efficiency. Okay, so there are two ways to do this. So maybe let me provide the first one. So now this is to check if S squared it's efficient. So the first method, so let me denote method 1. So the first method is still going to use our known information, which is we can use the n-1 S squared sigma squared. This one we already know that if following a chi-square distribution, degree of freedom n-1. Okay, so and then let me also write down the gamma distribution, which is the n-1 over 2 with the beta equal to 2. Okay, so instead of directly calculating the variance of S squared, in the first method, we can first calculate the variance of S squared, V squared, the V, which is the one that we already know is the chi-square distribution. Okay, and the variance of the V is the expected value for V squared minus the square of the expected value for V. And for these two terms, they can be easily calculated because we know that it follows a gamma distribution. And then from our previous derivation, we know that the expected value for V raised to the power of 2, which is the second moment, you can either use the formula for the gamma distribution, which is related to the x raised to the power of k, or you can use the moment function to calculate the second moment. And here I'm just going to directly write down the result, which is also from the lecture before. So the second moment should be equal to the alpha plus 1 multiplied by alpha beta squared. And this is for this alpha and beta. And this result you already have from your previous lecture. So this is the alpha beta that I'm referring to. Okay. So the second moment for a gamma distribution is equal to that, and the first moment is equal to the alpha multiplied by beta. And then you also have a square. So now we can simplify this by plugging the alpha and beta. So the alpha is n-1 over 2, and then plus 1, multiplied by n-1 over 2 for the alpha, and then multiplied by beta squared, so it's 2 raised to the power of 2. And then also minus n-1 over 2 raised to the power of 2, and then 2 raised to the power of 2. So this is just using the gamma distribution. And then this result is from the previous lecture. And then after you simplify this expression, let me give an intermediate step then. So n-1 over 2, and then plus 1, you can also do a plus 2 over 2, so that you can do that. And then n-1 over 2 multiplied by 4, so all the denominators should be cancelled out. And you also have n-1 squared over 4 multiplied by 4. Okay, and then after you simplify this, you should have 2 times n-1. So that is the variance of V. But what we really want is the variance of S to declare whether, or to check whether it's efficient or not. So we need to do some further manipulation to obtain the final result. Okay, so let me also put it here. This is the variance of V that we evaluate using the gamma distribution. And then the V is also the n minus 1 multiplied by S squared over sigma squared. And this S squared is the actual quantity of interest that we really wanted to talk about its variance. So now let's also look at this term here. So the n minus 1 over sigma squared can be considered as a constant. So when you move that outside the variance, you need to take the square. So n minus 1 square raised to the power of sigma raised to the power of 4. And then you have the variance of S squared. So this is the quantity that we are interested in. And we also know that this equation is also equal to 2 times n minus 1. This is coming from here that we derived from the gamma distribution. So now we just need to simplify or to move around the terms, and then we will get the quantity of interest. Variance of S squared, it's equal to, let's see, 2 times n minus 1, and then sigma raised to the power of 4 over n minus 1 squared. And this is equal to 2 sigma 4 over n minus 1. Okay, so that is the variance of S squared. And later, we will calculate the Cramer-Rao lower bound through the Fisher information. And then we want to compare the variance of S squared with the Cramer-Rao lower bound. And then if they are equal, then it's efficient. If they're not equal, then it's not an efficient estimator. Okay, any question up to this point? So the goal here is to get the variance of S squared. Okay. So that is for the first method. And then let's also briefly talk about the second method. And the second method is essentially because we have the distribution for S squared that we cover here. So if we know the distribution of S squared through the momentary function, then we may not, if you want, you don't need to use the method 1 to calculate that. The method 1 do not require that you know the distribution for S squared. But if you know the distribution for S squared as we derive here, then you can directly calculate the variance of S squared. So the variance of S squared, as we already know that the S squared following a gamma distribution, so that we can directly apply that it should be alpha beta squared. And then the alpha is equal to n minus 1 over 2. So n minus 1 over 2. And then the beta is 2 sigma squared over n minus 1. So 2 sigma squared over n minus 1. And then taking the square. So if we simplify that, we will get n minus 1 over 2, and then 4 times sigma raised to the power of 4 over n minus 1 squared. And then this should give you 2 sigma raised to the power of 4 and then n minus 1. So as you can see that from the first method, without requiring the distribution for S squared, and through some manipulation, we can obtain the variance of S squared equal to that. And the method 2 is that we know that the S square is following a gamma distribution with n minus 1 over 2 and then 2 sigma square over n minus 1. So if we know this result, then we can directly apply the variance formula to get the variance of S squared. But either way, you get the same result. The variance of S squared is equal to 2 times sigma raised to the power 4 over n minus 1. So here I'm just providing two methods to calculating the variance of S squared. Any question or comments? Okay. So now we have the variance of S squared. Now we need to develop the Cramer-Rao lower bound. And that is to compare with the variance of S squared to check or to determine whether it's efficient or not. So the Cramer-Rao lower bound for, let me complete. So we need the Cramer-Rao lower bound for sigma squared, because our S squared is an estimator for sigma squared. So we still need to derive the Cramer-Rao lower bound for sigma squared. So yeah, so here I just want to point out that the sigma square hat is not an unbiased estimator for sigma squared. So that's why we cannot discuss whether that is efficient or not. The efficient estimator has to be unbiased first. So that's why we need to compare the S squared, the variance of S squared with the Cramer-Rao lower bound. So it has to be an unbiased estimator to further to talk about whether it's efficient or not. So that's why we need to focus on the variance of S squared. Okay, so for the Cramer-Rao lower bound for sigma square, we need to go through the Fisher information. So again, there are also 3 methods to calculate the Fisher information. So it's up to you which one that you want to use. So here, I'm going to calculate the Fisher information for sigma square using one of the 3 methods. And particularly, I'm going to use the Hessian, which is the negative expected the Hessian for sigma square. And then for the Hessian is essentially the second order derivative of the likelihood function with respect to sigma square, which means we have the following. So we need to take the second order derivative. Let me put it twice here to emphasize that. And then the log likelihood function, which is the negative 1/2 log of 2 pi square, sigma square, and then minus a 1 over 2 sigma square, and then x minus the mu here. So we want to evaluate the expected value for the second order derivative for the likelihood function, which is essentially the Hessian. Okay. So all these are just a definition thing. And now we need to simplify this second order derivative. So negative expected value, let's take the first order derivative and leave one copy of another first order derivative for now. So for the first order derivative of this one, with respect to the sigma square, you will have negative 1/2. And then the chain rule, so 2 pi sigma square in the denominator, and then multiplied by another 2 pi. And then for the second term, because this is in the denominator, so you will have an extra negative 1 in the front, so this becomes a plus. and then 1/2 sigma square raised to the power of -2. So this is sigma square raised to the power of -1. When you take the derivative, you will have -1 sigma square raised to the power of -2. And then x and mu are constant because we are working with the derivative with respect to sigma square. So everything else should be considered as constant. So that we have a square, x minus mu square here. And then closing the expected value. Okay, so here, this is only the, let me put a square bracket as well. So this is the first order derivative. And we also need to consider another derivative to get the Hessian, as the Hessian is the second order derivative. So we have the negative expected value for another copy of derivative. So now we should have, because the sigma square is again in the denominator, so you have a -1 in the front, so that becomes a positive value. So 1/2 of, the 2 pi already cancel out, so you only have sigma square raised to the power of -1. So the derivative is sigma square, but raised to the power of -2. And then plus 1/2, and then -2 sigma square raised to the power of -3 from here. And then the constant term. So this expression is the second order derivative of the log likelihood function, which is the Hessian. And now we just need to simplify this form to get the final result. So the negative expected value, and let's see, we have 1/2 raised to the power of sigma raised to the power of -4, and then we have the minus sign here again, and the 2 is cancelled, so we will have sigma raised to the power of -6, and then x minus mu square, and then that. So let's see. So I think this is the simplified form, and now we just need to evaluate the expected value. Okay, so now the expected value is only going to work on the random variable. So our only term involving the random variable is the x minus mu. So that is the only term that will be affected by this expected value, and the remaining parts are all constant. So that means we have -1/2 sigma raised to the power of 4, as this is a constant, and then plus sigma raised to the power of -6, and then expected value for x minus mu square. Okay. And then because x is following a normal distribution with mean mu and the sigma square, and this thing here is essentially the definition of the variance for random variable x. So then you can replace with -1/2 sigma 4 plus sigma raised to the power of -6 multiplied by the sigma raised to the power of 2, which is the variance of x. And then you will get the following. So you have one copy of, did I miss? Oh, I missed a minus sign for the here. So now you have one copy of sigma raised to the power of -4, and then another -1/2. So you only have a +1/2 sigma raised to the power of -4. Yeah. So this is the Fisher information for the variance term, the sigma square. And now we need to get the Kramer-Rao lower bound. So the Kramer-Rao lower bound of the variance of sigma square is equal to the 1 over n times the Fisher information for that. So you will have 1 over, let's see which way is, so maybe I'll put so maybe I'll put 2 sigma raised to the power of 4, and then I put the n on the top. So I'm using n multiplied by the Fisher information here. So yeah, and then now you can take the inverse. You will have 2 sigma raised to the power of 4 over n, and this is the Kramer-Rao lower bound. Okay, so now we have that from the Fisher information. To finally check whether S squared is efficient, we need to check the variance of S squared. Variance of S squared from here is 2 over sigma raised to the power of 4 over n minus 1. And this one is actually greater than the Kramer-Rao lower bound. So 2 multiplied by sigma raised to the power of 4 over n. So you divide it by a smaller number, and that means this is a larger value. So this is greater than that, or you can also write this is not equal to that particular value. So S squared is not an efficient estimator, because it does not equal to Kramer-Rao lower bound, so it's not an efficient estimator. Okay. But however, for checking the consistency, so let me write it again. Variance of S squared is equal to n minus 1 to raised to the power of 4. So this will go to 0 as n go to infinity. So we can say that S squared is a consistent estimator of sigma square, or yeah. And here is not an efficient estimator of sigma square. Okay, so just to conclude, or to summarize our example, is that we have n samples of the normal random variables, and then we estimate the maximum likelihood estimator for both mu and the sigma square. And then we check that the maximum likelihood estimator for mu is an unbiased, efficient, and consistent estimator. But for the variance, for the maximum likelihood estimator for sigma square, which is not an efficient estimator. And then we come up with the S square, which is an unbiased estimator for sigma square. But the S square is not an efficient estimator, but S square is a consistent estimator for sigma square. So that is our conclusion here for this entire example. Okay, so is there any question or comments? Okay, so next I will talk about another topics, which is called the confidence interval. So the confidence interval, I think we have already talked about it before, which is referring to some other random variables. So the confidence interval here for our context is regarding the parameters. So let me put, so it's regarding the parameter theta, which is the parameter of your statistical models. So previously we talked about confidence interval for like a constructing all those like common distributions, like the T and the F and the Z distribution, the normal distribution. But now we're talking about statistical models. We can talk about the confidence interval for the parameter, which is the theta. So the confidence interval can be defined as the probability for this theta fall between lower bound and the upper bound with some probability 1 minus alpha. And this 1 minus alpha, people usually call this a confidence level. So you need to know you need to specify your confidence level to construct the confidence interval for your unknown parameter. So the theta is something that exists in the real world, but we don't get to observe. What we have is that we draw some samples, like we collect data from the real world. Like we ask people like their heights from the campus. We can only ask like the height of let's say 1,000 people, but this parameter is referring to the whole population in the whole world. But we don't have the luxury, or we can never know the parameter for the nature. So that's why we need to collect data point. We get the data point from 1,000, let's say, students, and then we use that as our samples to make inference regarding the parameter in the nature or for the theta that we can never obtain what exactly this value is. But we can use sample as a statistical methods to make inference regarding that parameter. Okay. So yeah. So for our first example, let's use the normal again. So here, let x1 to xn. Again, they are IID because each of the data points are independent of the other. So you can always think about if you ask a person their height and then you approach to a second person, the second person is independent of the first person. So you have the IID condition, and that's why we have our statistical tool like maximum likelihood estimator to perform this kind of a statistical inference. Okay. So IID from the normal, mean mu, and the sigma square. Okay. So here let's assume that the sigma square is known, and then we want to find the confidence interval for mu, the population parameter. So for confidence interval, we are always talking about the population parameter, and then the x bar is referring to the sample average, and then we are trying to use the data that can calculate the sample average to make inference of the population parameter that we don't know, or that we can never observe. So here, to construct the confidence interval, we have to start from our sample average. So we know that the each of the xi following a normal with mean mu and sigma square, and the average of the xi, which is the 1 over n sum from xi. So this one should also follow a normal distribution, as a linear combination of a normal random variables is also following a normal random variable. We already proved this using the homogeneity function. And then the mean for this x bar is just the n multiplied by mu over n, so which is also equal to mu. And then for the variance is the n times the sigma square over n square. So this is equal to the sigma square over n. So that is the mean and the variance for x bar given the mean. Okay. Yeah. So now we know the distribution for x bar. Now we are able to construct a confidence interval for the mu, so that we can construct the following. So the x bar minus the mu over the standard deviation. This one should follow a normal 0, 1. And then you can see that our parameter of interest, the mu is appearing in this formulation. And then we also know that this formulation is following a normal distribution. So we are going to use what we know of about the standard normal distribution to get the confidence interval. So the way to do that, coming from our definition, like the confidence interval here, we can write that this quantity x bar minus mu over sigma over square root of n is greater than the quantile, which is the negative z alpha over 2 less than z alpha over 2. So here is depending on your confidence interval. So if you choose a particular, let's say 95% confidence interval, then you can use the quantile for that, like 0.025 on the left hand side and then 0.975 on the right hand side. So the alpha is like a user specified parameter, so you can choose. But here we just write down the z with alpha over 2 as a general notation. And you know that this probability of this thing fall in between this two upper bound, lower bound has a probability of 1 minus alpha. So this is the reason why we can make the confidence interval, as we know that this thing follow a normal distribution. Yeah. So now we can construct our confidence interval by moving the terms around. So first of all, we can get the maybe let me keep the probability notation here. So we multiply by the denominator on all three terms. So you have the negative let's say z multiply by the sigma square over square root of n. And then in the middle, you only have the x bar minus mu less than the positive multiply by sigma over square root of n. And then you know that this event still has 1 minus alpha probability. So for example, you can put alpha, if you specify alpha equal to 0.05, then here you can find the 0.025 and then the 0.975 for the upper bound, lower bound, to have the center mass with the 0.95. Okay, so because we are manipulating the terms on all three this inequality, so the probability of this event is still going to have a 1 minus alpha probability. And now we can do our final manipulation by moving the x bar outside. So we will have the probability of x bar minus a z over alpha over 2 multiplied by sigma over square root of n less than mu. So actually here there's another step. So if you move the x bar on both sides, so if you minus x bar, you will have the x bar less than a negative mu less than x bar plus that. And then if you take the negative signs, and then you also need to flip the greater than sign here. So but they have the same conclusion, is that the mu is greater than this minus the z, and then less than the x bar plus the z alpha over 2 sigma square over square root of n. And this event still have the probability 1 minus alpha. So the things inside the parenthesis is called the confidence interval for the population parameter. So we don't get to observe. So this is the population parameter for the mu. And this thing is coming from the data. And in this example, we assume that the sigma square is also known. So when you plug in the data, and this one you also look up for the table from the normal distribution. So the lower bound and the upper bound are all known quantity. The only thing that you don't know is the population parameter mu, that you don't get to observe from the nature. So that by using this idea of confidence interval, you can make inference to say that, okay, the population parameter is in between this particular interval. Yeah, but in practice, the real parameter that you don't get to observe is either in or not in this interval. You don't know. So that's why you can only say that you are only up to a confidence interval. So you are only 95% confident that this unknown quantity is fall in between this range. So you always say that you are 95% confidence about this. But whether it's in this or not in this, you don't know. And then the population parameter is 100% in or 100% not in this interval. So you only have that confidence interval. The confidence level, you only 95% confident that this is in this interval. Yeah. But it could be in this interval, it could not be in this interval. Yeah. Okay. So next, for our example, we have okay, then maybe let me speed up a little bit. So for the second part is that, let's say sigma square is unknown. Okay, so then we need to consider two components. So x bar following a normal with mean mu and the sigma square over n. This is the parameter of interest, the mu. And because we don't know the sigma square, so we need to rely on another component, which is the n-1 s square over sigma square. This is following a chi-square distribution, degree of freedom n-1. Okay, so with the sigma square known, then you know that the quantity from the previous example following a normal distribution. But now the sigma square is also unknown, so you need to come up with another distribution. And that distribution, our choice of distribution is going to be t distribution. And then you can construct in the following way. So mu minus x bar minus mu over sigma over square root of n, and then divided by chi-square distribution n minus 1 s squared, and then sigma square divided by n minus 1, taking the square root. And this is the construction of a t random variable, which following a t distribution with degree of freedom n minus 1. So now you can use the same definition that, let's also simplify this. So this should be, if you simplify this form here, you will get x bar minus a mu over s divided by square root of n. And this thing is no longer following a normal distribution, but following a t distribution. And then you can, again, use the x bar minus mu over s divided by. So here, this is less than the t with the alpha over 2 level, and then less than the t with degree of freedom with the alpha over 2, and then also the degree of freedom n minus 1 and n minus 1. So when we know this variance sigma square, we can just directly use the normal distribution to get the confidence interval. But by removing one pieces of information, that the variance sigma square, that which is unknown, then you need to using some further statistical model to convert it to something that we know. So in our case is that we need to rely on the chi-square distribution to construct our t distribution to get our final confidence interval. So this thing, to have this events with 1 minus alpha probability, you will need to rely on the quantity from the t distribution, and the final confidence interval for mu here is going to be x bar plus t, the quantile for t for your confidence interval, multiplied by s over square root of n, and then x bar minus the confidence interval, the level for the t distribution, multiplied by s divided by that. Yeah. So by removing one information from the big picture, you need to bring up more statistical methods, which is the chi-square distribution into this picture to make it happen, or to make it valid to calculate the confidence interval. So you move away something, or you're missing some information, you need to rely more powerful or more component in statistics to get the same result. And also usually for t distribution, you will have a larger confidence interval because you have some component missing, the sigma square missing, so that your confidence is wider, so that you have more uncertainty regarding whether this component fall into your confidence interval or not. So that is the confidence interval without the sigma square. Okay, then for our last example, it's for a two-sample test. So here, in many biological experiments, you usually will encounter that you have two samples. One is before or after treatment, and then you want to tell that whether there's a difference between the two treatment group, and then you need to rely on the following to perform your analysis. So in this example, let x1 and xn coming from a normal distribution with mean mu and the variance sigma square. And then for y1 to ym, here maybe let's also put the variance, the mu1, and then you have the mean of mu2. So this is what you believe that your before treatment, the samples that you collect in your, say, biological experiments is coming from a distribution from mu1. And then let's say after treatment, you expect that, for example, your patient recovered, and then you assume that your patient or the samples is coming from another distribution, which is with the mu2. And here we are also making assumption that the variance is the same for the two groups. And then, but the variance is still going to be unknown. So actually, when you perform lots of the analysis, when you're making hypothesis testing in your, let's say, biological experiments, you are often making different assumptions. So in our case, the assumption is that the sigma is shared across the two treatment group, and also the sigma square is unknown. So this is the underlying assumption that you are doing, or people are doing for their hypothesis testing in the biological, let's say, trials or experiments. Okay, so our goal is to find the confidence interval for mu1 minus mu2. So we want to know that whether this difference, the confidence interval for this difference. And then one thing that related to the hypothesis testing is that, for example, if your lower bound, let's say for mu1 minus mu2, let's say this is a negative value and this is a positive value. So that means the 0 is included in your confidence interval. Then it is very likely that there's no significant differences between your before and after treatment group. So that if you do a hypothesis testing and you have the zeros in your confidence interval, that is very likely in another conclusion that you are going to reject your null hypothesis that there's effects for your drug or for your experiments. It's very likely that there's no treatment or there's no effects between the before and after treatment. So if your confidence interval has a 0 in it, it's very likely that you are going to reject your null hypothesis that this is not equal to 0. Yeah. So this is just another comments here. So the confidence interval is also very highly related to the hypothesis testing. You want to test whether there's effects before and after the treatment, so that if the 0 is included in the confidence interval, then there's a very high chance that the difference is also going to be 0. So there's no significant effects on this drug. Yeah. But that is a different story. So we want that, and then let's suppose the sigma square is known. Then you can just simply relying on the normal distribution. So x bar minus y bar minus mu1 minus mu2. Okay, so maybe let me take one more step back. So you know that x bar minus y bar following a normal distribution of mu1 minus mu2. And then the variance is sigma square over n plus sigma square over m. And then from the previous examples, you know that the confidence interval for you can construct the following. So mu1 minus mu2 over sigma 1 over n plus 1 over m. this is less than the z alpha over 2, z alpha over 2. So if the sigma square is known, then you can just directly using the normal distribution to calculate that. But in our case, sigma is not known. So, however, sigma square is unknown. So we are going to rely on the S square, which is an estimate for the sigma square, to construct the confidence interval. So to get that, we are going to rely on the maximum likelihood. So here I'm going to write the f of x1 to xn, and then because they are all independent, so I can put the y inside here. So y1 to ym, and then this is equal to 2 pi sigma square for the negative 1 over 2 sigma square summation from 1 to n, and then xi minus mu 1 square. This is for the x part, and the y part is for 2 pi sigma square negative m over 2 exponential of negative 1 over 2 sigma square summation from 1 to m, and then yi minus mu 2 square of that. Okay, so this is the joint density for x1 to xn from y1 to ym. And the reason for that is because when you're collecting your data for your biological experiments, all those trials or all those samples, or let's say the patients, are independent. So that's why you can construct this joint like a density function. That is because they are IID. And that's the reason why I can construct this. And our goal is to find the estimator for S square, to estimate the sigma square here as the two samples that we assume that they share the same variance. So we're going to use the likelihood or the maximum likelihood estimator to approach this. So let's see. So here I'm going to take the log of that, ends up with the lowercase, and then for the parameter sigma square, and taking the derivative with respect to sigma square. So now all four terms are going to also, maybe let me take one more steps. So you will have negative n over 2 log of 2 pi sigma square minus that and then minus m over 2 log of 2 pi sigma square. Okay, so just by taking the log transformation, and then everything becomes like in the the exponent becomes in the front, and then you have the log of those things, and then you cancel out the exponential operations here. You're just taking the log. Yeah. So that is the log likelihood, the joint log likelihood function, because you have all the n samples and all the m samples there. And then for the next step, we are just going to take the first order derivative with respect to the sigma square. Yeah. So when you take the derivative with respect to the sigma square, so here I'm going to combine these two together. So you will have the negative of n plus m over 2 sigma square. So this is from this component, and I group them together. And then you have the other component from here. This is equal to, let's see, so you should have 1 over 2 sigma raised to the power 4 sum of the xi's. And you also have the same thing for the yi's. This is for mu1 and then mu2. Okay, so this is the first order derivative, and then you want to set that equal to 0, and so for the sigma square. So you can multiply the sigma raised to the power 4 on both sides, or for all terms, and then you will end up with negative n plus m sigma square plus the sum of the xi's plus the sum of the yi's. Okay, and that is equal to 0. So now that there's only one term involving the sigma square, and then you will get your final expression for the sigma square hat is equal to the sum of xi minus mu1 plus I from yi minus mu2 divided by n plus m. Okay, so that is your maximum likelihood estimator for the joint case. And then here, I'm just not going to show you the proof, but the maximum likelihood estimator for mu1 and mu2 are just x bar and then y bar. And then we also know that the sample variance for the x variables are just the xi minus x bar square divided by n minus 1. And the same thing for y is divided by n minus 1. So then we can rewrite the sigma square hat equal to n minus 1, the sample variance for x plus the m minus 1, the sample variance for y, divided by n plus m. Okay. So one thing that maybe I'm not going to provide you too much detail is that the expected value for this thing, it's not equal to the true value, to the true sigma square. This is equal to the n plus m plus 2 over n plus m multiplied by the sigma. So it's not equal to sigma, so this is not an unbiased estimator. So we are going to define another thing called as pool. The pool is for pooling the two samples together. And then this pool variance, sample variance, will be very helpful for constructing your confidence interval for your two sample test. Okay, so the pool variance is going to be defined in the following way. It's just to multiply the inverse of that to correct the bias, n plus m plus 2 of the sigma hat. And then this, when you plug in this coefficient, this is equal to n minus 1, the sample variance for x, and the m minus 1, the sample variance for y, and then here divided by n plus m minus 2. So this is actually the formula that you often use for constructing a two-sample t-test. This is also called the pool variance. When you have two samples from before treatment and after treatment, and then you need to construct the confidence interval, then you need to use this pool variance to construct that. And this is the formula that you probably often use for your two-sample t-test. And the t-test, the t is also coming from the derivation that we are going to talk about now. So you have the x bar minus y bar minus mu1 minus mu2. Let's see. Oh, before that, maybe let me make one more comment. So here, one more thing is that this n minus 1 over sigma square following a chi-square distribution, degree of freedom n minus 1. So here, you can break this one as n minus 1 plus m minus 1. And so here you can have the n plus m minus 2. So I'm going to multiply the denominator on the left hand side as pool equal to n minus 1 s squared plus m minus 1 s squared. And then now I'm going to divide it by sigma squared for everything. So here you will know that, you will see that this thing following a chi-square degree of freedom n minus 1, this thing following a chi-square degree of freedom n minus 1. And then they are equal after we correct the bias by multiplying this factor here. So, and then x and y are independent. So then you know that this one following a chi-square distribution n plus m minus 2. So this is that the new component that you define, and then you know that this following a new chi-square distribution. So the previous version, the not unbiased one, you do not have that information regarding the distribution. After you make the correction by multiplying this factor, you have this expression, and then when you move the denominator on the left and then divide it by the sigma square, you know the distribution for this one by pooling all your data points together. So that's called a pool variance. So the P is referring to the pool. So you pool everything together by pulling two samples before treatment and after treatments. And then you have the distribution assumption that you can apply. Okay, so now we can just construct our confidence interval. So x bar minus y bar minus mu1 minus mu2 divided by the variance from the beginning here. So sigma multiplied by 1 over m and then 1 over m. So this is going to be a standard normal z that follow a standard normal. But we don't know the variance, so it has no practical values because you cannot use that for a biological test. And then you need to introduce one more, which is the chi-square distribution, so that you will have the n plus m minus 2, the S pool divided by sigma square. And then you know that the distribution for that is the chi-square with degree of freedom n plus m minus 2. So you can also divide it by that, taking the square root. Okay, so finally, this thing, the whole thing, should now follow a t distribution, degree of freedom n plus m minus 2. So this is the distribution that you often use for your two-sample t-test. And then the trick or the core component is that you need to pool all the variations from your two samples together to obtain this S of pool. And then it allows you, or it allows the scientists to perform this two-sample t-test. And then the t is coming from that this is following a t distribution. So, and then we kind of also just prove that this is following t distribution. Okay, and then for the rest, it's just the same thing. So when you simplify this expression, you will have x bar minus y bar minus mu1 minus mu2 divided by, so after you simplify this form, you have the S pool in the denominator, 1 over n plus 1 over m. That. And this thing still following a t distribution, so you have a negative t quantile here, and then a positive quantile here. And then the rest is just moving around the term. You will have your confidence interval mu1 and mu2, mu1 minus mu2. The population difference is in between your data set, the one that you get from data, plus t alpha over 2, the S pool. So here there's no more square because you take the square root, and then 1 over n plus 1 over m. And then same thing for here, minus the t alpha over 2. And this is the formula that you often use in your two-sample t-test, or if you do some biology experiments, you will always using this t-test. And this is the derivation, or kind of like the proof why it is t and why it can be used to construct the confidence interval. And then if you want, you can also use this to construct to perform hypothesis testing for your null hypothesis. that your H0 is that this one equal to 0, and then your alternative is not equal to 0. But that's a different story. But it also fall align in this framework. Okay, so that will be the confidence interval. So maybe let me stop here, and then to conclude our discussion for estimator and also confidence interval. And as you can see that when you construct the confidence interval, you also need to use this maximum likelihood estimator to help you to find some estimator that can be used for confidence interval.